This video is part of a series in which we describe how a simple microcontroller core can be implemented in System Verilog. In this video, we'll be looking at the memory in which both the program and the data are stored, and we'll go over the memory module. The EveCore architecture was designed to be implementable with a Harvard architecture computer. In the Harvard architecture, both the program memory and the data memory are separate. The program is presumably kept in a read-only flash memory, while the variables in the stack are kept in a volatile random access or RAM memory. This distinction between program memory and data memory is very typical of many microcontrollers. The architecture has instructions for accessing the program memory and instructions for accessing the data memory. For example, we have load and store instructions, and these instructions take a 16-bit address, or have as part of the instruction a 16-bit address, and the load instruction goes to the data memory, fetches a byte, and moves it into one of the 8-bit registers, while the store instruction takes a byte from one of the 8 registers and moves it into the data memory. We also have the load M and store M instructions. In these instructions, the address is computed as the sum of the M register and an offset. The M register is a 16-bit register, and a 16-bit offset is included directly in the instruction, and these are added together to compute an address in the data memory. And in the case of the load M instruction, a byte is moved from data memory into the A, or accumulator, register, and in the store M instruction, a byte is moved from A into the data memory. We don't have a load or store instruction for the program memory. We don't have a store instruction for the obvious reason that the program memory is considered to be a flash, read-only flash memory, and so we can't store anything into it. We don't have a load instruction for the following reason. Presumably, when we program the chip, that is when we flash the memory, we know exactly what bytes we're putting into the program memory. It doesn't really make sense to go to the program memory to fetch a byte if we already know ahead of time what that byte is. It makes more sense to use a move immediate instruction. The move immediate instruction simply moves the byte itself into one of the 8-bit registers. By the way, the load instruction is also 3 bytes long. It takes an opcode byte plus 2 bytes for the 16-bit address, while the move immediate instruction is only 2 bytes long, one for the opcode and one for the immediate 8-bit value. Sometimes, though, we do need to compute an address in the program memory, and for that we have the load code instruction. For example, the program memory might contain an array or a table of values, and we might want to index into that table or array to fetch one of the values. So the way we do that is compute the index into the table or array and put that in the XY register. The XY register is another 16-bit register, and the load code instruction will use the value in the XY register as a pointer into the program memory, and it will fetch a byte and move that into the A register. So both of these memories can be up to 64 kilobytes in length, so we have 16-bit addresses. We have no special addresses within either the program or data memory. We have no regions that are set aside for special uses. The address 0 in program memory is slightly special because that's where program execution begins. And the stack grows down from high memory, so the stack is going to be located at the top of the data memory. But other than that, there's nothing special about this. Now, one of the neat things about the EveCore architecture is that it can also be implementable on a von Neumann architecture machine. So in a von Neumann machine, we only have one memory, and it stores both the program and the data. And so if that's the implementation of the EveCore architecture, then all these instructions that we've just described all work on just the memory. So that's pretty straightforward. And so we can implement the EveCore architecture either on a Harvard machine or a von Neumann machine. And so now let's take a look at how we're going to implement the memory on our implementation. My initial plan was to take the Harvard approach and have separate memories for the program and the data. So I would have 2 modules, one for the RAM and then a module for the ROM, such as the one shown here. And my plan was to make the ROM purely combinational. And that's what we see in this module, right? It takes an address as input and it provides the data byte as output. And as you can see, it's purely combinational. There is no state in this module. So for any given address, it just does a lookup to determine what byte to return. And I went to quite a bit of trouble to program the assembler so that it would produce output like this. In fact, this output is copied directly from the assembler's output. You feed in a source program, and the assembler spits out Verilog statements that are shown here. And you just do cut and paste straight into the system Verilog code, and voila, you've got your combinational ROM memory module. The problem with this is that this kind of system Verilog code eats up lookup tables. This uses a lot of lookup tables. The FPGA we're working with doesn't have a whole lot of lookup tables, and this is just not a feasible approach. We're going to have to do something different. So we're going to go with the von Neumann approach, where we have a single module that will handle both the program memory and the data memory. In the Harvard approach, we've got two modules, a ROM module for the program memory and a RAM module for the data memory. But in our case, we're just going to have this single module called memory, and it's going to handle both the program and the data. They're going to be stored together. So now let's take a look at how this module works, and we'll start with the interface. We've got a 16-bit address going into the module, and we've got 8 bits of data coming out. So we'll use this for reading the memory. We can also update the memory. So we've got a single line called write enable. We'll raise that and provide the data in, which is 8 bits, whenever we want to write the memory. This is a clocked module, right? It has state. So there's a clock input as well as our clock enable, which is used for doing single stepping. So this module does have state, and that's given right here with this memory array. Each element of the array is an 8-bit byte. And how many elements do we have? Well, that's given by this parameter here. I've just set it to half a kilobyte, which should be enough for the programs we're going to be concerned with. And now let's take a look at the meat of this module. So on the rising edge of the clock, we do something if the clock enable is high. And what do? Well, in all cases, we go to this memory register and retrieve a byte given the address input here, and we copy that to data out. Data out is now a register, so notice that we put the address in on one cycle and we get the data out on the next cycle. With the ROM module I just showed you earlier, that was combinational, so the data is coming out on the same cycle that the address is going in. But now we've got this one cycle delay. We've also got the ability to update the memory. So if the write enable line is high, then we update a byte in this array using the 8 bits of data input that we've got coming in here. You can also see that we're making a call to this function called read memory. This is not really something that gets executed at runtime, but this is used by the system Verilog tools that compile our system Verilog code. And so in our case, the Lattice Semiconductor tool, or whatever it is you're using, will hopefully recognize this function. This function takes 2 arguments. One is the name of a file, and the other is the name of the register array that we want to be updating. So it will go to this file and get a bunch of bytes, and it will use those to initialize this memory array. And this function is put into the initial block or some initial code like I've shown here. And when the tools build our FPGA, it will access this file. And then when we download or flash the FPGA, the registers will be initialized to whatever values were in this file here. Where does this file come from? Well, I showed you earlier that the assembler that I wrote is capable of producing system Verilog statements, and it can do that, but it can also produce raw hex data. And so I used the assembler that I wrote to compile or assemble a small program, and it produces output in a form that's appropriate for this read memory function. This read memory function expects the data to be just a sequence of hex values that are given in ASCII form. So each byte of the hex data is represented with 2 ASCII characters with 1 byte of data per line. And so that's the format that the assembler produces. And then when we use the tools to compile our system Verilog code, it will access that file and initialize the memory register. The software tools will look at this module and recognize it as a particular form. It's an idiom, or it's in a standard form that the tools will recognize, and instead of using registers and lookup tables and logic cells to implement this module, it will instead use block memory. So every FPGA contains some block memories, a number of blocks of RAM memory, and that memory can be used whenever the tools recognize a module such as this one. So this module is in a special format, a format that allows the tools to recognize it, that it should be using that block memory. The combinational approach that we talked about earlier had the problem of using up a bunch of lookup tables, and when the tools look at this module, they will use the block memory to implement this, which is a much more efficient use of the FPGA resources. A few lookup tables will of course be used, but the number of lookup tables will not be dependent on the size of the program. They will not be dependent on how many bytes are loaded into the memory, and so that's definitely a win. Now I'm using a single module for both the program and the data storage. It's certainly possible to use 2 different modules, one for the program memory and one for the data memory. We could create a ROM module that would look just like this, except it wouldn't have the write enable stuff, and it wouldn't be able to update. So this part of it would be missing, and the software tools would recognize that and put it in block RAM, or BRAM as it's called, and that would be fine. We would have 2 different modules, and the program and the data memories would be separate. Some instructions will access the data memory. All instructions will have to access the program memory because they have to fetch the opcode, and in some cases they have to fetch additional bytes of instruction. And so if you have separate program and data memory, then those accesses can perhaps be done simultaneously, and that could save a few clock cycles. So that is one advantage of the Harvard architecture. The accesses to data memory and to program memory can be overlapped. With the von Neumann approach, we're going to have to sequence those. We're going to have to do those one after the other. And so for some instructions, we will have to have a few additional cycles. But I figure that it's better to go with the von Neumann architecture. If you take my code and use it for your own application, and you are very concerned about cycle counts, and you decide to improve efficiency by separating out the memory into a separate memory for the program and a separate memory for the data memory, then you're welcome to do that. Or maybe you're going to implement this architecture on a chip where you will have flash memory for the program and RAM memory for the data. I think it's probably easier to separate out the architecture, that is to transform a von Neumann design into a Harvard design, rather than to start with a Harvard design and try to combine it into the von Neumann design. So that's why I'm going to take the von Neumann approach with a single module. And so this is our memory module that we'll be using. And that's it for this video. I will see you in the next video.